Good morning, everyone. Today we are continuing our discussion of our non-Mendelian genetics. So we've covered things like incomplete dominance and having multiple genes, and today we are going to be talking about something called polyallelic. If polygenetic means multiple genes, then you should be able to figure out that polyallelic means multiple alleles. And as a result, you will get 3 or more phenotypes. But unlike when we had our incomplete dominance, with this one, we're not going to have a blend. So there's no middle phenotype. For example, in the game, we have our drake tails. And the way that those tails work is you have long tails are dominant to kinked tails, and kinked tails are dominant to short tails. So I'm going to write this in a new way. I'm going to say that the tail gene can have a long allele, or the tail gene could have a kinked allele, and this would result in a long tail. If I had long, that would also be long. Now, if I have a tail with a kinked allele and a tail gene with a short allele, that's going to be kinked. And the only way to get a short tail is to have TS, 2 of the short tail alleles. Now, when we're looking at this, kinked is not a middle version between long and short. It is a totally different phenotype, which means that it's not a blend, which means that I can tell, even though there are 3 different phenotypes here, I can tell that this is not an incomplete dominant situation. Because those characteristics are distinct from each other, this is a polyallelic situation. In humans, we have our HLA markers. Because if you remember, you could have like HLA A25 and you could have HLA A12. And you have 2 of those, and that's going to create your HLA markers. The next thing that we're going to be looking at is codominant. And in codominant, you also have 3 or more phenotypes. But all of the alleles are shown in the phenotype. And this one doesn't really come up in the game. So our example is going to be from chickens. There are some chickens that have feathers that are all black, and there are some that have feathers that are all white. And our black feathers we're going to label with a B, and our white feathers we're going to label with a W. And so we're going to use our code again here, where we have the gene is labeled and then the alleles are labeled separately. So I'm going to use F for feathers, and if they have 2 of the black alleles, then all feathers are black. And if they have 2 of the white allele, all feathers are white. But chickens can also have 1 of each. And if they have 1 black and 1 white allele, then they have half of their feathers are black and half are white. And this also happens in humans. And it happens with our HLA markers. Not only are there multiple alleles for our HLA markers, so you could have like 12 or 29 or 44 or 126. There are multiple alleles. All of those are numbers. They have a whole range of numbers. But because you only get 2 of them and both of them show up on your cells, your combination could be something like 1229, or your combination could be 4429. And both of those are going to show up. So your HLA markers are both polyallelic and codominant. The next thing that we're going to look at are sex-linked genes. And these are genes on the X or Y chromosome. Normally on the X chromosome. Our example of this in the game is faded and deep. And in the game, having a deep color is dominant to having a faded color. So deep is the dominant one. So let's see what happens when we have our different parents. So moms have 2 of these X chromosomes. So a mom that has X chromosome little d, X chromosome little d, is going to be faded in color. That's the way that she'll have the recessive trait. For dad to have the recessive trait, because he only has 1 X chromosome, and then he has a Y chromosome, he only needs 1 copy of that recessive allele to have the recessive faded phenotype. Moms can also be what we call a carrier. And a carrier is someone who has 1 copy of the allele for the trait, so 1 copy of the recessive version, but they don't have the recessive phenotype because they also have a copy of the dominant version. So let's see how this plays out in terms of what offspring are going to be produced. So let's see what happens when mom has that recessive trait. So when mom has the recessive trait, I'm going to need to draw my Punnett square here. And I drew it kind of wide because we've got multiple letters that have to fit in here. So dad does not have the trait. Mom does. So here, I'm going to make a girl because it's going to be X, X, and again, another girl, X, X, where this X is from dad and this X is from mom. Here are my boys. And what we can see here is that 0 of the girls have the trait, but 100% of the boys have the trait. And that's what we often see with sex-linked traits where they're on the X chromosome, is that it's going to be way more common in boys, because boys are going to be able to always get that from their mom, whereas girls, their dad can give them the dominant version, which covers it up. All of these are carriers. So let's see what happens when one of those girls has a baby. So now we're going to say mom is a carrier. So same Punnett square setup. Dad still does not have the trait. And now mom is a carrier. So she does not have it on 1 and she has the recessive allele on the other chromosome. This girl doesn't have the trait, isn't a carrier. This daughter is a carrier. This son doesn't have the trait. This son does have the trait. So let's highlight these just for ease. So here has the trait, has the trait, has the trait. So what we see now is, again, 0% of the girls have that recessive phenotype, and 50% of the boys have the recessive phenotype, but neither of our parents showed that recessive trait. So this often gets passed along. Mom doesn't even know she's a carrier, dad doesn't have it, but their sons end up with this trait because they only get one copy of that X chromosome from their mom. Let's see what happens when dad has the recessive trait. So mom doesn't have the trait, and she also is not a carrier. Dad has the recessive trait, but again, he only needs one copy of that because he has a Y chromosome instead of two X chromosomes. So here we've got carriers for daughters, but again, 0% of the girls have the trait. And 0% of the boys have the trait. So even though dad had that recessive trait, he was unable to pass on that trait to his boys because he doesn't give them an X chromosome, and he was unable to pass on that trait to his daughters in a way that showed up because mom is not a carrier.